Welcome to Module 35 of the course on pericyclic reactions and organic photochemistry. In this particular module, we will consider two topics mainly: photoreduction and singlet oxygen photochemistry. In addition to that, we will also see some miscellaneous photochemical reactions at the end of the module. Now let us start with the photoreduction process. Photoreduction of carbonyl compound is a very popular reaction in photochemistry. In the n-pi star excited state, carbonyl oxygen subtract hydrogen atom. This is typically we saw it in the Nourish type 2 reaction in the earlier module. This is essentially reduction of a carbonyl functional group. Therefore, in the presence of a suitable hydrogen donor, the reduction of the carbonyl group can be accomplished under photochemical condition. When the carbonyl excited state abstracts a hydrogen from a hydrogen donor source, it gets reduced. In the process, you can reduce a carbonyl functional group to the corresponding alcohol, or quite often the pinacol is what is formed. In this example, benzophenone is reduced under photochemical condition when the reaction is carried out in the presence of, for example, isopropyl alcohol, cumene or hexadiene of this kind, for example. These are hydrogen donors. They donate the hydrogen to the carbonyl oxygen, thereby producing a benzhydryl radical. The benzhydryl radical undergoes dimerization to give the pinacol. The mechanism of the reaction is discussed in the next slide. Initially, benzophenone undergoes photoexcitation to the n-pi star excited level. The n-pi star singlet state is what is initially formed. Because aromatic ketones have very high efficiency of intersystem crossing, they go to the corresponding triplet state. In the triplet state, the carbonyl oxygen behaves like a alkoxy radical, and it abstracts the hydrogen from the alpha position of isopropyl alcohol, in other words, alpha to the hydroxy functional group. This particular hydrogen is abstracted in the formation of the benzhydryl radical. After the abstraction of the hydrogen, a diradical is formed, and this particular diradical, namely dimethyl methyl hydroxy methyl radical, is capable of further reducing another molecule of the benzophenone to the corresponding benzhydryl radical, and in the process isopropyl alcohol has lost two hydrogens, which corresponds to acetone. So isopropyl alcohol in the process gets oxidized to acetone. The benzhydryl radical thus produced is reasonably stable to look into another benzhydryl radical in terms of the dimerization reaction. So photochemical dimerization is a very efficient process under this condition. In fact, if you mix benzophenone with in isopropyl alcohol with a drop of acetic acid to remove any amine kind of impurities and leave it under sunlight, the benzpinacol gets precipitated out of the reaction mixture quite readily. So this is a sort of a light driven reduction reaction of the benzophenone to the corresponding pinacol as the final product. Benzophenone bearing electron donating groups unfortunately do not undergo this reaction for two reasons. It could be that the electron donating group, for example, if you put a methoxy group or a phenyl group on the para position of the benzophenone, the higher excited state, the lowest excited state becomes a pi star excited state. Under the pi star excited state, the carbonyl oxygen does not have the ability to abstract the hydrogen from the alcohol or the hydrogen donor. Similarly, in the case of 4,4' dimethylamino benzophenone, which is known as Mischler's ketone, this particular structure is what is referred to as Mischler's ketone. This, upon photoexcitation, actually undergoes an intramolecular electron transfer. So the excited state is actually a charge transfer state like this, and this is not capable of abstracting a hydrogen atom from a hydrogen donor. Therefore, benzophenones bearing electron donating group could be either going to a pi star lowest excited state, which is not a hydrogen abstracting state, or it could be a charge transfer state, as in the case of the Mischler's ketone. So it is hard to reduce the benzophenone with electron donating group. Benzophenone itself or benzophenone bearing halogens or nitro or cyano functional groups readily undergo the hydrogen abstraction reaction, followed by reduction to give the benzhydryl radical, which dimerizes to give the corresponding pinacol. Now, the ketone reduction can also take place in the presence of tertiary amines, for example. Here is an example of a photoreduction of a carbonyl functional group using electron transfer mechanism. The reaction mechanism is fairly simple. The benzophenone initially undergoes photoexcitation to give a singlet n-pi star state. It undergoes efficient intersystem crossing to give the triplet n pi star excited state. The triplet n pi star excited state is a good oxidizing agent. So it oxidizes the tertiary amine to the corresponding cation radical, and in the process it gets reduced to the corresponding anion radical. So this is benzophenone anion radical is what is produced. The benzophenone anion radical abstracts hydrogen from a proton is transferred from the methyl group of the tertiary amine to the O minus here, producing benzhydryl radical. In the formation of the benzhydride radical is triggered. The benzhydryl radical, as usual, undergoes dimerization to give the corresponding benzpinacol as the final product in this case. So this mechanism is very different from the earlier mechanism, which does not involve any kind of electron transfer process. For example, it is a mere hydrogen abstraction followed by dimerization kind of a mechanism, whereas in the presence of a suitable electron donor like the tertiary amine, which is dimethyl aniline in this particular case, it goes through an electron transfer mechanism via a radical ion pair, for example, and followed by the formation of benzhydryl radical, and dimerization is the mechanism. So two distinct mechanisms have been discussed for the photoreduction of benzophenone in this particular module. Now let us move on to photooxidation, in other words the chemistry of singlet oxygen in this particular instance. The chemistry of singlet oxygen is characterized by the fact that the triplet oxygen is the ground state electronic configuration of the normal oxygen. For example, atmospheric oxygen is actually a triplet state molecule. This is the electronic configuration of the triplet state of the ground state, which is a T0 of the normal oxygen. The nearest excited state is a singlet state, and that is about 22.5 kilocalories above the ground state, for example. And there is one more accessible singlet state which is about 37 kilocalories per mole. In fact, this wavelength corresponds to 1270 nanometer of excitation. This wavelength corresponds to 762 nanometers of wavelength of excitation. So in fact, the oxygen, normal oxygen, absorbs in the visible region. In the blue region is where it absorbs, for example. Sorry, the red region is where it absorbs. This is a near infrared region, whereas this is an infrared region, for example. So this is a visible region, and this is a near infrared region where the singlet oxygen, triplet oxygen absorbs. So the electronic configuration clearly tells you that this is spin unpaired, so this is a triplet state. This is spin paired, although the occupancy is in two different orbitals, whereas this is spin paired in the same molecular orbital. In fact, if we look at the occupancy here, the pi star molecular orbitals x and y are filled up in the S1 state, and pi x square is filled up, for example, in the S2 state. So therefore, in the excited state, namely in the singlet state, for example, the singlet oxygen should behave like a normal O double bond O kind of a molecule, whereas in the ground state the triplet oxygen should behave like a diradical kind of a state. So this is a representation of the ground state of the molecular oxygen. This is a representation of the excited state of the molecular oxygen, this particular case. Now let us have a look at the kind of reactions that singlet oxygen can undergo. Before that, let us see the production of singlet oxygen. Singlet oxygen is mostly conveniently produced by dye-sensitized reaction. In other words, a suitable sensitizer is excited to the higher excited state, singlet state, and this kind of dyes do have a very high intersystem crossing efficiency, go to the corresponding triplet state. The triplet state essentially undergoes an energy transfer to the triplet state of the oxygen, which is the ground state oxygen, producing the singlet molecule back, sensitizer back, and in the formation of the singlet oxygen, which is the excited state oxygen in this particular case. Dyes like rose bengal, methylene blue, and this particular aromatic compound, they are extremely efficient singlet oxygen producing dyes. Singlet oxygen can also be produced by the decomposition of endoperoxide. This is an example of an endoperoxide. In fact, the endoperoxide is produced, as you will see later, is by the reverse reaction of a singlet oxygen by diphenyl anthracene by a Diels-Alder kind of a reaction to produce the endoperoxide. However, the endoperoxide upon heating essentially releases a singlet oxygen back. Similarly, phosphine ozonides also undergo decomposition to give phosphine oxide and singlet oxygen in the process of decomposition. Although this is possible, in the practical usage this is seldom used because of the fact that it is much more easier are much more convenient to produce a singlet oxygen from oxygen itself by the dye-sensitized reaction that is shown here. Now let us look at the characteristic reactions of the singlet oxygen. Singlet oxygen with very rich electron-rich olefins, for example, undergoes a 2+2 cycloaddition reaction. This is a this is a thermal 2+2 cycloaddition reaction of an excited state oxygen with electron-rich olefin to produce this kind of a peroxy dioxetine kind of a molecule is what is produced, for example. On the other hand, with the suitable dienes like the diphenyl anthracene or hexadiene, the singlet oxygen undergoes a Diels-Alder kind of a reaction. The Diels-Alder reaction essentially produces the endoperoxide in this particular case. Again, in the case of the hexadiene also it produces an endoperoxide. In all of these cases, the photolysis essentially is the photolysis of the dye, which generates the triplet excited state, which in turn transfer or sensitizes the singlet oxygen triplet oxygen conversion to singlet oxygen by energy transfer mechanism. So in the last example, 2,5-dimethylfuran is reacting with the singlet oxygen, forming a ozonide kind of a molecule. This is as an ozonide of hexadiene, for example. So these are some characteristic examples of reactions of singlet oxygen with olefins and dienes and so on. Wherever there is a allylic hydrogen present in the system, it undergoes ene reaction. Singlet oxygen typically is a enophile and it can undergo ene kind of a reaction. In this particular case, the mechanism is fairly simple. It is a 1,5 hydrogen shift kind of a reaction to the oxygen with a concomitant formation of a carbon-oxygen bond to produce the hydroperoxide, which is shown here. In other words, the hydrogen from the methyl is transferred onto the oxygen and the oxygen-carbon bond is formed in forming the allylic hydroperoxide kind of a molecule. Wherever there are two sites possible, there are two allylic sites possible in this particular molecule. One site is here, the other site is over here. In fact, the equal amount or nearly 70-30 ratio of the two products are formed. The more substituted olefin is formed, for example, because the hydrogen transfer from a more substituted carbon is more facile compared to a less substituted carbon. That would explain the product distribution of these two hydroperoxide that are formed in this particular reaction. This is terpene derivative. It undergoes singlet oxygen ene reaction by reacting with this allylic hydrogen over this position, resulting in the formation of the allylic hydroperoxide, which is obtained in nearly quantitative yield in this particular instance. Now let us look into some miscellaneous reaction which we did not look into earlier, and this is essentially the reactions of the carbonyl functional group. In this particular example, the carbonyl functional group is a highly constrained cyclopropene kind of a fused cyclopropene kind of a system. It undergoes decarbonylation reaction under photochemical condition, resulting in the formation of a highly strained acetylene. This kind of acetylene cannot be produced by chemical methods. So in order to produce this reactive intermediate, for example, one can do a photolysis of this highly strained cyclopropenone derivative, resulting in the formation of this acetylene. This acetylene, of course, will undergo dimerization, 2+2 cycloaddition kind of a dimerization to give the butadiene kind of a molecule. This is a highly substituted butadiene, so this is reasonably stable compared to the butadiene itself. It does not undergo further cycloaddition reactions. Here is a nice example of a tetrahexamethylene 2,2,1 bicycloheptane, for example. It undergoes decarbonylation reaction to produce a 1,4 diradical. Please bear in mind this 1,4 diradical is a highly conjugated diradical system. Such reactive intermediates can be studied in a frozen matrix using spectroscopic methods, for example. Either a EPR spectrum or a UV visible or an infrared spectroscopy can be done on this kind of a system under frozen matrix condition. The tertiary butyl substituted ketone, this tricyclic ketone, for example, undergoes decarbonylation to produce what is known as tertiary butyl tetrahydrane. This molecule is a tetrahydrane. The unsubstituted tetrahydrane itself is not a known compound. The tertiary butyl substituted tetrahydrane is a known compound. It has been synthesized by a photochemical reaction involving the decarbonylation reaction of this particular ketone that we have here. Here is another example of the 2+2 cycloaddition reaction. In other words, this is an example of a synthesis of a fruit fly attractant. This is a fruit fly attractant which is a pheromone that is secreted by the fruit fly, for example. This is done by initially doing a 2+2 cycloaddition reaction, which is the Pattern-Nobuchi reaction. So the carbonyl undergoes a 2+2 cycloaddition reaction with the olefin to produce this particular oxetine as the product. These subsequent reactions are of course synthetic transformation to get the fructactant, which is the E isomer of this olefin alcohol is what is given here, for example. So how is it done? This double bond is reduced. Hydrogenation of the double bond results in this formation of the saturated compound. Under thermal condition, oxytanes can undergo ring opening reaction. So essentially this bond and this bond are cleaved to give the oxygenated product in this particular instance, resulting in the formation of a ketone. The ketone is reduced to the alcohol, and in fact the alcohol is the fruit fly attractant in this particular case. There is another moth repellent is also produced. Instead of taking cyclohexadiene, if you take heptene, cycloheptene as the molecule, the same kind of chemistry will result in the formation of a larger chain system alcohol that is actually a moth attractant or moth repellent, for example. So synthetically, the photochemical reaction 2+2 cycloaddition reaction is an extremely useful reaction to produce the oxetine. Oxetines can undergo ring opening reaction by decomposition of the cleavage of these two bonds here, resulting in the formation of the aldehyde, which is reduced to alcohol in this particular case. The reaction of a beta dicarbonyl compound's enol form, the addition reaction of an enol of a beta dicarbonyl compound is called a De Mayo reaction. De Mayo reaction, if you look at, this is a simple reaction. You consider acetyl-acetone as the starting material. Acetyl-acetone can exist both in the keto form as well as in the enol form. When it is irradiated in the presence of cyclohexene, it is the enol form which is undergoing a 2+2 cycloaddition reaction to give the cyclobutane. So cycloaddition across this carbon-carbon bond here and this carbon-carbon bond results in the formation of the cyclohexyl fused cyclobutanol as the product. Now this is nothing but a beta hydroxyketone. If you look at this, this is alpha and beta. So in the presence of a base, one can do a retro-aldol kind of a reaction to produce this diketone. What have we done in the process? We have essentially bisected the acetyl-acetone. The acetyl part of the molecule is attached to one carbon of cyclohexane, and the acetone part of the molecule is attached to another carbon. So this is essentially a very convenient way to produce this kind of 1, 2, 3, 4, 5, 1,5 dicarbonyl compound. 1,5 dicarbonyl compound can of course undergo a further aldol condensation reaction to give cyclohexenones as the product. This example is the synthesis of this larger ring system is illustrated by the example of dimethone. Dimethone is nothing but dimethyl cyclohexadione. This exists in the enol form, which undergoes a cycloaddition process again with the cyclohexene, resulting in the formation of the fused system. The fused system is a ketone, which is a beta hydroxyketone. Again, retroaldol reaction essentially results in the formation of the cleavage of this particular bond, resulting in the formation of the 8-membered ring with 2 carbonyl functional group that are shown in the relative positions in this final structure, for example. So this is a nice way of synthesizing a 8-membered diketone, which is a regioselective synthesis, for example, in this particular case. Here is an example of a gamma hydrogen abstraction followed by trapping of the exomethylene intermediate. If you take this is alpha methyl or orthomethyl benzophenone. Orthomethyl benzophenone under photolytic condition will produce the corresponding dienol because of the hydrogen abstraction from the ortho position. The methyl group gives a hydrogen to the carbonyl oxygen in the excited state, resulting in the formation of a quinodimethyde kind of an intermediate. If the quinodimethyde is not trapped under the dark reaction, in other words, in the thermal reaction, it will undergo hydrogen migration, otherwise ketoenol tautomerism will take place, essentially resulting in the formation of the benzophenone back. However, when the reaction is carried out in the presence of a dienophile, like the dimethylacetylene dicarboxylate, for example, the trapping of the diexomethylene or the quinodimethyde derivative is trapped. This is an intermediate which is trapped by the dienophile, resulting in the formation of a Diels-Alder reaction to give this alcohol, for example. The same reaction, when it is carried out in the absence of any kind of a trapping agent dienophile, but in the presence of oxygen, initially the hydrogen abstraction results in the formation of the quinodimethyde derivative hydroxy hydroxyquinodimethyl derivative. Hydroxyquinodimethyl derivative is a triene system. If you look at this as a pi electron system, this is a 6 pi electron. It undergoes under photochemical condition a 6 pi electron cyclization, resulting in the formation of a dihydroaromatic derivative. The dihydroaromatic derivative essentially undergoes oxidation in the presence of oxygen to give the aromatic derivative. In other words, anthrone is the product that is formed under the reaction condition. The same kind of reaction is also extended in the case of the heterocyclic system, which is this particular system, to synthesize isoquinoline type alkaloid in this particular instance, for example. This is an exomethylene derivative. The nitrogen lone pair can be delocalized onto the carbonyl functional group, thereby establishing a double bond kind of a character between the carbon-nitrogen bond. In other words, the amide has a double bond character. So this is acting as a 6 pi electron system, undergoing a 6 pi electron cyclization to produce the dihydroaromatic, which is in this particular case a stable compound. So this is resulting in the formation of the isoquinoline kind of a isoquinoline alkaloid kind of a structure is what is obtained in this particular case, for example. The same methodology is extended to yohumbane kind of alkaloid, which has this particular skeleton, and there are several examples of this kind of alkaloids have been synthesized using the photocyclization kind of a reaction, which is a 6 pi electron cyclization in all of this. So this newly formed bond will be this particular bond in this case, this particular bond in this case, and this particular bond in this particular case. This would be a furan substituted derivative which is undergoing a cyclization instead of a benzenide derivative, resulting in the formation of a dihydrofuran at the end of this ring. These are two regioisomers that are formed in the reaction when this position is occupied by a furan during the course of the 6 pi electron cyclization of this reaction. Lastly, we'll look at an interesting synthesis of a terpenoid molecule, which is in the racemic form. It is formed under the synthetic conditions that are going to be shown here. This is accoradiene. This is a terpenoid molecule. The synthesis of the molecule essentially starts with this particular enone, which has a built-in enophile in this particular case. So the 2+2 cycloaddition reaction of the enone with this olefin essentially produces this constrained fused cyclobutane derivative. In other words, think of a reaction between this center and this center that will produce the spiro 5-membered ring system, and between this carbon and this carbon essentially produces the 4-membered ring system. So this is a spirocyclic ring system with the 4-membered fusion is what is being formed by the 2+2 cycloaddition, intramolecular 2+2 cycloaddition of this type. Once the cycloaddition is over, now this methyl group here is oriented in such a way that you can have a alpha, beta, gamma hydrogen abstraction can take place. This is the gamma methyl group. So under photolytic condition, gamma hydrogen abstraction takes place to produce the corresponding diradical intermediate. This diradical intermediate of course can undergo decomposition reaction by delocalization, by the breaking of this carbon-carbon bond, resulting in the formation of an enol and the exomethylene compound. So this methylene essentially is coming from the formation of a CH2C carbon-carbon double bond here with the breaking of the cyclobutane derivative in this particular instance. This is further synthetically transformed into the alpha accoradiene in the racemic form by the sequence of reaction that is shown in this particular frequency. So what we have seen in this particular module is the example of photoreduction of benzophenone to benzphenacol by two different mechanisms. One is involving a hydrogen abstraction reaction, the other one involving an electron transfer kind of a mechanism. Then we looked at the electronic configuration of singlet oxygen and the production of singlet oxygen by dye-sensitized reaction using typically triplet dyes which have a long-lived triplet state so that it can be quenched by the singlet oxygen, by the molecular oxygen, which is triplet oxygen, to produce the corresponding singlet oxygen. We also saw several reactions of the singlet oxygen species in terms of its cycloaddition reaction and ene reaction. Finally, we saw some miscellaneous examples of photochemical reactions involving carbonyl reduction, involving 6 pi electron cyclization, and finally an enone cycloaddition reaction as an example. I hope you enjoy this module. Thank you very much for your kind attention.